Hello, AP Calculus AB. We're now over halfway done with our Topic 6 applications of integration and differential equations. In particular, we're done with our applications of integration, and we are moving on to our first day out of maybe 3 or 4 of differential equations. We've actually done differential equations before, we've just never really defined them as such. We actually even defined them one time, but that was so long ago that it's probably worth repeating. So let's get to it. A differential equation is any equation which contains derivatives. A differential equation with the first derivative being the highest derivative, meaning there's no second derivative, third derivative, so on and so forth. I always think of it as a ladder, right? If you have y and then y prime, y double prime. If the highest derivative in here is y prime, then it is known as a first order differential equation. If there are derivatives up to the second derivative, then you have a differential equation of the second order, and so on and so forth. Now, when you're asked to find the solution to a differential equation, your goal is to find the original equation, and let's keep in mind that this original equation should be in the form of y equals f of x, which means it should be y equals stuff happening to x. So a y isolated on the left side and lots of stuff happening to x on the right side, which has the given differential equation, or maybe which satisfies the given differential equation. So before we learn or review, because we've actually done this before again, how to actually solve a specific type of differential equation, and you'll learn further on in mathematics there are many types of differential equations. Let's make sure we know how to check our work, or maybe check to ensure an answer is actually correct. This is actually how most new equations are introduced to students. It's not let's solve it, it's here's how we check our answer, now let's solve to make sure we can get that answer. So here's a nice example. Verify that y equals 4e to the 3x sine of x is a solution to this differential equation, right? This is a solution because it's in the form of y equals f of x, and this is a differential equation because it has a derivative, right? It has y prime. It's a first order differential equation over there. How do we verify? Well, instead of trying to solve this, when you verify solutions, you substitute your solution back into the original equation. Yeah? So what does that mean here? Well, let's take a peek. I think we could probably try some substitution, and maybe I should actually touch more on that substitution. So let's say I asked you to solve 3x plus 1 equals, I don't know, let's make this interesting, equals 13. And I said, I think x equals 4 is the solution. Okay, well, to check it, although you could solve this, the check is actually involved with substituting 4 into our equation, doing the math. 12 plus 1 is 13, and we verified that 4 is a solution because the left side equals the right. And that's exactly what we're going to do here. So to verify that this guy is a solution to this differential equation, I'm going to start with the differential equation. I'm going to go ahead and put this guy over here. So dy dx equals 3y plus 4e 3x cosine of x. And we're going to start doing some replacements. Most commonly, what you guys are going to do today is you're going to replace anything that has a y in it to be in terms of x. So I see two different y's here. I see a y that's over here, and I see a y buried in this dy dx. So we need to replace each of those with our solution. Now one of those is pretty easy to replace. The y that's right here, and I'll maybe run out of room here. Sorry, I probably should have spaced this differently, but that's all right. This y is easy to replace because we know what y equals. Y is equal to 4e to the 3x sine of x. Cool. But how about this dy dx? How can we replace that? Well, if this is my solution, then couldn't we use the solution and create dy dx? Okay, so to do that, we find the derivative. We find d dx of the left side and d dx of the right side of this original equation. Y equals 4e to the 3x times sine of x. And I accentuated the times because when you do the derivative of two functions multiplying, oh yeah, that's right, you need the product rule. The left side is pretty easy. This is just dy dx. The right side, though, can be a little complicated, so note the product rule that I'll delineate with two different colors. 4e to the 3x, hopefully we're comfortable knowing that e to the 3x is itself. The 4 is multiplying, so that stays as well, but we do need to do the derivative of the power, which is that extra 3. Sine of x doesn't change yet, and then we add on. We keep the first one the same, and then we do the derivative of sine, which is cosine. Oops, wrong color there. Second try. Alrighty. From here, now we have found dy dx. So what do we do with that? Well, we substitute all of this in for dy dx, and I was very lazy there and just drew an arrow. Now, do those two match? Well, if I drop the parentheses on this left side, I'll keep it in blue since I boxed it in blue. This first piece over here, 4 and 3 makes 12, so I'm seeing 12e to the 3x sine of x, and then plus 4e to the 3x cosine of x. And the question becomes, is that equal to what's on the right side? Well, this is 12e to the 3x sine of x plus 4e to the 3x cosine of x. Are those equal? They are. And so we have proved that this is a solution because when we substituted it or its derivatives into the original differential equation, the left side equaled the right. In fact, you might have seen this notation before. Sometimes it's common to put 3 equal signs to say that this is an identity with these two, right? And we've seen this when we proved trig identities before, and you're like, oh my gosh, are we doing trig identities? Not really. I mean, there is a bit of a connection in that you have to manipulate this to make it match over here, but mostly it's just take a few derivatives and plug it in. But it's the same concept. We're showing that this left side is equal or identical, really this is our identical sign, is identical to the right. Now, that above question could have been asked in a bunch of different ways. It could have said, instead of verify that this was a solution to dy dx, it could have said that verify 4e to the 3x sine of x is a solution to y prime. In fact, y prime is generally more common just because it's fewer things to write. You could have even moved things around here, right? We could have moved everything over to the left side by subtraction and said verify it's a solution to y prime minus 3y minus 4e to the 3x cosine of x equals 0. And when you substitute everything into the left side, guess what happens? Oh, right, it equals 0. The method is still the same, though. Find any derivatives that are asked for and plug them into the differential equation. Now, some of these seem like they're pretty straightforward, right? These differential equations. You might have looked at this first one and said, well, if this is the derivative, maybe I could just like take the antiderivative of each piece and somehow that would give me back for this as an original answer, right? If we start with dy dx and we work back to y, isn't that just an antiderivative? And some of them are that simple. However, I think you'd be very hard-pressed to be given this differential, this second-order differential equation, and say, hey, guess what y equals? And you're like, there's no x's in there. What do you mean, what does y equal? And then the look on your face when you realize that y ends up equaling something with sine and cosine, you'd be like, whoa, 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 whoa. Where do sine and cosine come from this nice, beautiful little second-order differential equation? Now, we're actually not going to learn how to do that this year, even for the next couple of years. There are whole courses dedicated to solving these. You'll take differential equations if you go in the math or engineering route. You might take partial differential equations. There's a second course to that. There are many different ways to solve these, but again, we are not doing that this year. We, to start, are just verifying solutions. And then we'll learn one way to solve these. So, let's rock and roll. Verify this is a solution to that. Well, we already know y. That's pretty easy, right? We know we can substitute y with that guy. But we do need y double prime. Oof. And so to find y double prime, let's start with y prime. Okay. Y prime is just the derivative of this. We have 4. Derivative of cosine is negative sine, so I just tack the negative onto the 4. Inside stays the same times 2. plus 6 cosine of 2x, derivative of the inside is times 2. So we'll clean that up slightly. Looking at negative 8 sine of 2x plus 12 cosine of 2x. Nifty. Once we're here, though, since we want y double prime, we need one more derivative. Negative 8, derivative of sine, which apparently I'm struggling with today, times 2, plus, nope, this is going to be derivative of cosine, so that'll turn to a minus sine of 2x times an extra 2, and finishing the cleanup process, negative 16 cosine of 2x minus 24 sine of 2x. All right, now that we have this, let's start our substitution. So we'll go through and we'll say we are beginning, and the equals 0 I'm just going to kind of stack over here, and then as we need to substitute things in, right, we will. So I'm just going to space things out. So we have y double prime plus 4 times y equals 0. And this will kind of let us line everything up. So y double prime here is being replaced with negative 16 cosine of 2x minus 24 sine of 2x. Excellent, that worked out just fine. Plus 4 times y, and this one I am going to run out of room. Oops, awkward. Don't forget your parentheses. 4 cosine of 2x plus 6 sine of 2x. There we go. And all of that is equal to 0. Can we clean this up? Well, I hope so, because in order to be a solution, this left side better equal the right. So I think we can probably, we'll write everything out once more. Probably easier to do more on this, and you can always fast forward at 2 times speed if you'd like. Let's see, so 4 times 4 is going to give us 16 of these cosine of 2x's. And then 4 times 6 is 24 sine of 2x. Has to equal 0. Hopefully some things start to cancel, and I think they do. Negative 24 sine of 2x undoes the positive 24. Negative 16 undoes that. If they all disappear, it just leaves us with 0 equals 0. Thus, it is proved, QED, it is identical, and we are very excited. Now, it is important to realize that because of the plus c that occurs when you take antiderivatives, there can sometimes be more than one solution to a differential equation. Case in point, you guys have 6 problems to practice on this next page, and anything you don't finish is your independent practice for tonight. I do have solutions to this posted on Teams, so I'm not going to go through it with you. But look at these 2 differential equations. We have a second-order differential equation right here, and we have another one right here, and those are exactly the same. But I said one of those solutions is here, and another's here, and those are not the same equation, 2 very different graphs. In fact, that's going to be common all the way through, right? Here's a second-order differential equation with a solution. Here's the same one with a different solution. So it's really just helping you see that you can have definitely different different solutions to the same differential equation. So take a bit of time, try verifying each of these identities. It's very good derivative practice, and then we'll get into the second part of today whenever you are ready. All right, hopefully you've had enough time to get through this. You've checked your solutions. Let's get to the second part of today. It's one of my favorite concepts in all of calculus, and it's really easy. Promise. If you see one of these problems, these are called slope fields, on a free response, you should be happy. Happy, happy, happy. So here we go. What is a slope field? Well, we'd already discussed what a differential equation was. It's any equation that contains derivatives. Our goal when we find the solution to a differential equation is to find the original equation in the form, again, of y equals f of x that matches that given derivative. And first-order differential equations that only have x in it are pretty easy, right? For example, if we were given this differential equation and we said y equals what has that derivative, it shouldn't be too bad, because we can just take the antiderivative, can't we? The antiderivative of 3x squared is just x cubed. And I would suggest that this is a solution to this differential equation, because when we take the derivative of x cubed is 3x squared. However, that's not the full solution. We've seen before if there's no limits of integration, we do need to add on a plus c. Now visually, what does that look like? Well, If you graph y equals x cubed, that is of course our usual cubic graph, looks something like this. But what does plus c do to a graph or do to a family of functions? So doesn't it shift it perfectly up? And so if we graphed an infinite number of these with different values of c, you would see, no pun intended, these graphs shifted up and down, but that look almost identical. You maybe even say, oh, they're all parallel to each other. It's kind of weird being parallel but not linear functions, but either way, we get the idea. And so that's a little bit of an interesting idea, understanding that although y equals x cubed is one graph, y equals x cubed plus c is an infinite number of graphs shifted up and down. A slope, or sometimes it's called a direction field, is a tool that we can use to visually see the solutions to a differential equation. Now this is useful in two different ways. First, you can use this graphical tool to check your algebraic solution, right? You're going to be able to graph whatever your solution is, and if it fits into your slope field, if it fits the pattern, then you're going to say, oh, I was right because it follows my slope field. But the other reason that this is so powerful is because many differential equations are really difficult to solve. In fact, there are some that you might even not algebraically be able to solve. But if you can at least visualize the solution, you can get a general idea of what that curve or what that equation is supposed to be, and then find the equation that way. So, how do we do this? Well, to graph a slope field, you need to understand the meaning of a differential equation. So let's look at a new example. dy dx equals x. And although one way you could interpret this is the rate of change as y changes over x is the equation x, we could also think of this in terms of every individual point on a coordinate plane. And we could think of this as the slope, right, dy dx, at every point on the original graph is the x coordinate of that point. So if you look at the point 4, 2 on the original graph, what would the slope be? Well, the slope is the x coordinate, so the slope is 4, or 4 over 1 if you want to rise over run. If you looked at the point 7, 2 on the original graph, even if we don't know what the original graph looks like, we know that the derivative or the slope is 7 over 1. So what a slope field does is it goes to every individual point on our coordinate plane and it graphs a tiny slope at each point. And once you put all those tiny slopes together, you will see a picture of the graph. So how does this work? Well, you're going to be given a blank graph with a whole bunch of points put in. My graphing software, by the way, doesn't like points that are on the axes, so if you would take a quick second and put in some extra points right here, I keep meaning to fix that, but this year was not the year. So, looking at this, it seems as though we have, what is this, 1, 2, 3, 4, 5, 6, 7, 7 by 7, we have 49 points here. Okay, then once we see those, and this will be given to you, you don't have to put all those individual points on there, we need to find the slope at each point. We know how to find the slope because we're told that the slope at every point is the x coordinate. So for example, if I look at this point right here, this is the point -2, right? We go over 2 and up 3. So -2, 3. And because the slope dy dx is x, is the x coordinate here, then I know that the slope right at this point on the original graph is the slope of a line that is down 2 over 1. Same thing, I know at this point on the x-axis is the point 2, 0, so I know the slope here is up 2 over 1. All right, well, how does that help us? Well, what we're going to do then is we're actually going to graph a small slope, a line with the slope that goes at each point. Okay, so I'm actually going to use this slope field up here because it's not scattered with all these little numbers down here. I just wanted to show the numbers to show what each slope was. So let's do a few together. For example, let's try the point 1, 0. 1, 0 has a slope of 1, as we can see down below. How do we graph a slope of 1? Well, if you picture a line that has a slope of 1, that means go up 1 over 1, up 1 over 1. This is a line that goes out at a 45-degree angle. Anywhere on the line has a slope of 1. And so I'm just going to try and match that at this slope, or at this point of 1, 1. It is an approximate, and look at the dots. You can kind of see that 45-degree angle, and we're just going to do a little line like so. It's not super long. It goes maybe, I don't know, a quarter of the way, an eighth of the way to any point in each direction, and it just needs to show an approximate 45-degree angle. It's not going to be perfect. You aren't graded on doing exactly 45-degree angled slopes. And in fact, you can be clever here because we know that every point with an x-coordinate of 1 has a slope of 1. So this point up here, 1, 3, also has a slope of 1. So just try to match what you did before, something like that. In fact, I think all of these have slopes of 1, don't they? Okay. Well, what about moving backwards and looking at all the points on the y-axis? This is the point 0, 1. The x-coordinate is 0. It has a slope of 0. What do lines look like with a slope of 0? They are horizontal. And so the slope of 0 is horizontal, like so. Let's look at 2 more. Let's look at the points that are 2, something, a slope of 2. And you might say, well, a slope of 1 is easy, right? A slope of 1 is just kind of, between 2 points, 45 degrees easy. What do I do with a slope of 2? Well, with a slope of 2, you have a couple options. You can look at the next point that's a slope of up 2 over 1 and say, ooh, I want to point up there. Or you can just make it a little steeper than a slope of 1. Right? So a little steeper than a slope of 1, I don't know, might be something like this. All of these are going to have a slope of 2, aren't they? You never have to go too far. So usually you're given between 9 and 12 points on a slope field, not 49, just between 9 and 12. And you have to fill those in, and there might be a couple with a slope of 1, a couple with a slope of -1, a couple with a slope of 2, maybe 1 or 2 with a slope of 0, and bam, you're done. So there aren't going to be a ton with like, here are 2 with slopes of 1, and then 2, and then 3, and then 4, and then 5, and you're like, I can't make it any steeper, they all look the same. No stress there, just a little bit steeper than the one before. So here's my slope of 2. Okay. Don't forget negative slopes, negative 45 degrees, something like this, right? There we go. So why don't you guys take some time, fill in the rest of these. I'll do the same thing, and then we can start to compare our graphs. All right, it's looking pretty good. Again, it doesn't have to be perfect. Oh, I forgot one. Slope of 1. There we go. Great. Okay, now what do you see? Hopefully you're just saying, oh, I just see a whole bunch of like weird lines. There's kind of a pattern there, but that's about it. Well, let's go ahead and talk about how we use a slope field to visualize the solution to a differential equation. Okay, we go through and we essentially just follow the slopes. Okay, so we are going to notice that each line segment, of course, has a slope corresponding to its x-coordinate. And you'll also notice that in my graphing software, I drew more than 49, right? You can see all these ones here. Mine drew more than that because I wanted you to see a clearer picture. Well, what happens if you just trace? If you kind of just follow the path of one of these lines like so, what shape do you see, right? If you just follow the way that the slopes tell you to go, don't we kind of see parabolas here? Well, then I think what this means, if we trace this and we see a whole bunch of parabolas, that our solution to the initial differential equation is a family of parabolas vertically shifted up or down. And that shouldn't surprise you, because if you see dy dx equal to x and you wanted to find the antiderivative of each side, right? Maybe treat dy dx as y prime. The antiderivative of each of these, antiderivative of y prime is y. Antiderivative of x is 1/2 x squared plus c, right? Isn't that the family of parabolas that's slightly vertically compressed, a little bit wider than normal, and shifted up and down, right? Each of these is 1/2 x squared plus some constant. So without even having to do an antiderivative, just being able to interpret our differential equation, we were able to draw a picture that showed us what the antiderivative or what the solution looked like. Okay. Now, sometimes they do ask you for a particular solution, right? If they ask you for the particular solution, we'll do this one in green, the particular solution passing through 0, 0, then what they're doing is they're essentially giving you what the constant is. Now, they're not telling you the constant, but they're saying whatever the constant is, made the parabola pass through, and I'm putting 0, 0 right here. You start at the given point, and then you just trace along the slope field to create the picture. And to do that, some people are like, wait, do I like perfectly try and like follow each of these? How do I do that? It's like squiggly. And the answer is no. Really, you just generally freehand as it goes through. I kind of just try and like travel actually between them, and I find that it looks pretty good, right? I just kind of go between like this, and that's fine. Some other people try to connect as many of them as they can, and they're like, I want to do like this, and that's totally fine as well. Whatever works for you. You don't get dinged on your super accuracy here. Okay? So, what are some practice problems going to look like? Well, let's look at one right now. To the right is a slope field for the differential equation dy dx equals x squared. Okay, I gave you a whole bunch of slopes there. Part A says draw a possible graph for the differential equation that passes through the points 0, 2. 0, 2 is up here. To visualize the solution to this, we just, give or take, follow our pretty slope field. It's kind of like connecting the dots. Great, that's all there is for A. So it looks to me like this is kind of like an x cubed graph, and that shouldn't surprise you too much, because if you solve this, if you go backwards from y prime equals x squared, antiderivative, add 1 to the power, 1/3 x cubed plus c, right? I think that does match our slope field. In fact, we could even go a step further and say, hey, we have the initial condition. We know y is 2. We know x is 0. And so 2 equals c, which tells us that y equals 1/3 x cubed plus 2 is the exact equation of the solution to this differential equation, which passes through 0, 2. And that's really about it. So on these last 2 pages, you have 2 problems that, or I'm sorry, you have 6 problems, 3 per page. Every problem includes 1 slope field and then 1 sort of bonus question. This one has 2 bonus questions for fun. So I'm going to go ahead and just do 1 of these with you, and then you guys have the rest to work through. As always, solutions are posted, and that's that. So let's take a look at AB 2004. Okay. These are almost always non-calculator active. There are way too many calculator programs these days that'll draw slope fields for you, but they are also usually some of the quickest free response questions to go through. So you should be really excited if you see a slope field. They are easy points. All right, A. On the axes provided, sketch a slope field for the 12 points indicated. Okay. Well, if we look at this guy, it says the slope is found by taking the x-coordinate, squaring it, and then multiplying it by the y-coordinate minus 1. So this differential equation is dependent on both the x and the y coordinates. Okay, so let's take a look at maybe this easy one, 0, 0 down here. And I tried to leave you a little space. It won't be a ton, but a little bit. We're going to find dy dx of 0, 0. Take the x-coordinate, square it. Take the y-coordinate and subtract 1. Mental math, 0 times -1 is 0. In fact, I think 0 times anything is 0, which means that this first part of our slope field has a horizontal slope, a slope of 0, right? Well, since the x-coordinate being 0 is going to turn everything to 0, then I think any point with an x of 0 is going to have a slope of 0, which 0, 1, 0, 2, and 0, 3 all have. It's a terrible horizontal slope. There we go. Nice. We can oftentimes use this to simplify this process too. So let's go ahead and see anything else that will turn this to 0. I think when y is 1, won't that turn everything to 0 as well? Let's verify that. Let's verify that with the point, I don't know, maybe 1, 1 that's right here. I'll do that underneath. 1, 1. All right, so dy dx at the point 1, 1 is the x-coordinate squared times 1 minus, or the y-coordinate minus 1. That's 1 times 0, which is 0. Yes. And so, because anytime the y-coordinate is 1, that's these 3 points, we can do some more horizontal slopes. Just a couple slopes to go. Let's try this point 1, 0. So dy dx at 1, 0, we get the idea. Now, you do not need to show this work for every point. If you can do it on your head, that's fine. You're just expected to fill in the little teeny tiny slopes here. So take the x-coordinate, square it, y-coordinate minus 1. I see 1 times negative 1, which is a slope of negative 1. So 45-degree angle going down. You also might notice that negative 1, 0 is going to give you the same result, because if this is negative 1 squared, it still turns into positive 1. This square means whether the x is positive or negative of the same value, you'll get the same answer, which tells me that whatever the slope is here, the slope over there is the same. Whatever the slope is here has the same slope on the other side. So we just have 2 more. That's super exciting. Let's do this one next. So this is the point. What is that point? 1, 2. All right, so x-coordinate squared, 2 minus 1. I'm seeing 1 times 1, which is a slope of 1. All right, horizontal, and I know that this one will have the same. You can test it if you don't believe me, but negative 1 squared, still 1. Last one, we'll do it up here. This is the point 1, 3. All right, x-coordinate squared, 3 minus 1. We get 1 times 2, which is 2, just a slightly steeper slope. And that's that. There's our slope field, right? Not too bad. I mean, it's just easy math, just plugging things in and knowing how the slopes are supposed to look. I should probably put the other negative slope over there. Great. Part B, last part for today, and then you guys get the practice. While the slope field in Part A is drawn at only 12 points, it is defined at every point on the xy plane. So I think what that means then is that you could extend this axis out and there would be lots of slope field, or lots of little slopes all the way through. Our goal is to explain where all the points are for which the slopes are positive. Okay, well, you'll notice down here we have negative slopes, so definitely not there. Here you have 0 slopes, so not there. But up here you have a bunch of positive slopes. So how can we describe where all the slopes are positive? Well, slopes become positive when the derivative becomes positive. So maybe let's start there. We're trying to determine where is the derivative positive. And we know the formula for the derivative, don't we? We know that x squared times y minus 1 has to be positive, yeah? Okay, well, going further, isn't x squared always positive? I think it is, isn't it? So that really doesn't matter for our equation, right? X squared is always going to be a positive. The part that determines whether our slope is positive or negative is the y minus 1. So how does that become positive? Well, isolate y, add 1 to each side. Y is greater than 1. I think, and logically it makes sense, looking at this formula, as long as the y-coordinate is larger than 1, won't this entire equation or expression on the right side become positive? And so, although it would be okay to leave it here, I always prefer a sentence, right? So, any point with a y-coordinate greater than 1 will have a positive slope. And that's it. So you have a few more of these to do, and hopefully you don't find them too terrible. There are a couple tricky ones, and you'll definitely want to go through and check my solutions on there. As a heads up, Part C on here uses the second derivative test. We did that all the way back in semester 1 in our topic 4. You may need to reference that. But the rest of these I think are pretty easy. And if you do have questions or if I made any mistakes, feel free to let me know. Next class, we're going to get into how to actually solve some of these differential equations. Not all of them, but some of them. And then we are on the downhill slope to spring break. So great job, guys. I'm excited to have you back for day 87.